Good evening. On behalf of Engineers Australia, I'm delighted to welcome you all to our Infrastructure Thought Leaders series on interlocking and permeable paving. My name is Amanda Rogers and I will be your host for tonight. Firstly, in keeping with our tradition, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders, past, present and emerging. In tonight's webinar, our speakers will discuss the engineering design principles for permeable and interlocking segmental paving. They will identify how to design permeable pavements to maximise the potential benefits from this currently underutilised paving system and share international case studies. Before we get started, I'd like to acknowledge that tonight's seminar is being hosted with our industry partner, Austral Masonry. Austral Masonry is one of Australia's largest manufacturers of concrete masonry blocks, retaining walls, pavers and stone products. Austral's innovative solutions can be seen on their high-end architectural projects and landscaping designs. Their commercial solutions include large-scale segmental block retaining wall products and permeable segmental block pavement. Austral takes pride in its products, which are of the highest quality and both durable as well as beautiful. I'd also like to invite you to join Brickworks for their exciting new spring-summer product launch, streaming live on brickworks.com.au. Designed to inspire and inform, it's your opportunity to have an exciting first look at the latest and most innovative products from Brickworks. For more information, you can find the link listed below in the description box. I'd now like to welcome our first speaker, Professor Simon Beecham. Simon is the former Deputy Vice-Chancellor for Research and Innovation at the University of South Australia, UniSA. Prior to this, he was Pro-Vice-Chancellor of the Division of Information Technology, Engineering and the Environment at UniSA. Simon's research is outcome-focused. He believes we need to be more sustainable in the management of our water resources. To this end, he has, through his research, been the author of industry available tools, such as the Siphon and Switch2 software programs. The Siphon model has been used to design the siphonic roof water harvesting systems at the Sydney Olympic Stadium, the Sydney Cricket Ground, the MCG and the new Adelaide Oval. It has also been used to design the roof drainage systems at the Hong Kong, Kuala Lumpur, Sydney and international airports in terms of iconic Australian buildings. The Siphon software has been used in the design of the Federation Square and Docklands redevelopments in Melbourne, as well as the new Royal Adelaide Hospital and the Adelaide Convention Centre. Wow. Simon is a Fellow of Engineers Australia, as well as a Fellow of the Australian Institute of Company Directors. Please join me in welcoming Professor Simon Beecham.
Hello everyone, my name is Simon Beecham and I'm from the University of South Australia, or UniSA, which is based in the city of Adelaide in South Australia. I'm delighted to be able to share with you our research on green infrastructure and particularly our work on interlocking and permeable paving. Following my presentation, my UniSA colleague, Associate Professor Mizanur Rahman, will discuss and demonstrate DesignPave, which is the newest Australian software tool for the design and analysis of interlocking and permeable pavements. Then Shushu Zhang from Becker will share her practical experience of designing innovative heavy-duty pavement systems, including airfield applications. But before I begin, I would just like to run over some of the terminology of this area, which can be a little confusing. I'll start with interlocking concrete pavements, block pavements. Whether engineered pavements are impermeable or permeable to rainfall, they are all designed to be interlocking, which means that rotation and wedging of pavers induces horizontal forces, which in turn results in load sharing. Edge restraints are also important to prevent lateral movement. You'll see this interlocking in action during a video that we'll be showing later in the presentation. The interlocking results in a very strong pavement system, as Shushu Zhang will demonstrate later in this webinar. The left-hand picture in this slide shows the construction of the IMEX terminal at Moorebank in Sydney. These impermeable systems are known as interlocking concrete block pavements, or ICBPs, while the individual pavers themselves in that left-hand picture are called concrete segmental pavers, CSPs. The right-hand picture shows a permeable pavement system in Adelaide, and these are known as permeable interlocking concrete pavements, PICPs, but this is often abbreviated to simply permeable pavements, or PPs. Note that they are generally bedded on different materials, the impermeable, permeable and the permeable pavements. So the left-hand picture, you'll see sand in the background, and the pavers are bedded purposefully on that sand, which can be compacted quite well. The impermeable systems in the right-hand picture are bedded on gravel, not on sand. Fine gravel, but still larger particle sizes than sand. Note also that the pavers themselves in both pictures are made from exactly the same material, solid impermeable concrete. In this vertical profile of a permeable pavement system, the pavers are the more common rectangular type with 5mm slots in the sides that allow water to infiltrate into the bedding course and then the base course, where it can either infiltrate downwards into the groundwater table, or it can easily be stored in the base course for later reuse. I'll demonstrate how this reuse is done a little later in this presentation. In terms of the design of either interlocking concrete block pavements, the impermeable pavements, or permeable pavements, this is rather complex unless you use a design software tool such as DesignPave. As an illustration, this is the design flowchart for a simple ICBP. CMAA, with great foresight, saw this as an impediment to the adoption of this innovative technology, and so they commissioned UniSA to develop what is the world's latest and most sophisticated software program, DesignPave. The Concrete and Masonry Association of Australia, or CMAA, is the peak industry body representing Australia's concrete masonry manufacturers. The CMAA funded UniSA to develop the new DesignPave software, which was authored by my colleague, Associate Professor Mizanur Rahman. Later in this webinar, Mizanur will demonstrate the software, which can be downloaded free of charge from cmaa.com.au. The DesignPave program designs both impermeable and permeable pavements and has customizable user inputs. It produces engineering reports for consenting authorities. It can conduct a cost and design evaluation, and as I mentioned, it's free to use. Uptake of this program since it was released 18 months ago has been very rapid. We have 539 current downloads as of last month, and some of the companies that are currently using the software are shown on this slide. So in terms of engagements, either with the program or with the supporting workshops, in the council arena, we've engaged with 17 councils and over 150 separate participants. And in terms of engineering consultancies, 31 consulting firms and over 300 participants. I'd like to now focus on 3 recent projects, 2 in Sydney and 1 in Adelaide, that were using the new software tool DesignPave. The first is the very recent 3,000 square metre upgrade of interlocking pavers. You remember these are the impermeable ones, along one of Adelaide's busiest and trendiest streets, King William Road. King William Road was first constructed with ICBP in 1985. The paved road was 2.2 kilometres long and was and still is the longest and oldest length of urban arterial road in Australia to utilise concrete segmental paving. Last year, it was reconstructed as shown in the colour photograph. Note that the original interlocking concrete block pavement lasted for 35 years, even though its original design life was probably 25 years. This is the reconstructed pavement today. The second project is the Leppington Bus Depot. Leppington is one of the first suburbs to be part of the southwest growth area of Sydney, and this project represents part of the public transportation services upgrade. The project consisted of 2,000 metres squared of building facilities, 7,000 metres squared of impermeable concrete segmental paving, and two 500 metre square permeable concrete segmental paving pits. All the runoff from the 10,000 metre square site was diverted into the two permeable pavement pits. Permeable pavements were used to allow designers to maximise the total hardstand area for the bus company. By using permeable pavements, designers were able to reduce site discharge below the council threshold of 88 litres per second for a 5-year design storm and 165 litres per second for a 100-year design storm. Additionally, the permeable pavement base acted as an underground detention basin, achieving the on-site storage capacity requirement of 200 kilolitres, as specified by the council. This was achieved without constructing large above-ground water storage infrastructure. From an environmental viewpoint, the project also used a variety of recycled materials. For instance, the base of the interlocking hardstand used blast furnace slag, a waste byproduct from the manufacturing of steel. Recycled sand was used as the bedding sand layer for the interlocking pavers, and the pavers themselves were manufactured with a cementitious replacement in the form of fly ash, a byproduct from the combustion of coal at power stations. This project also demonstrates the advances that have occurred in mechanical laying of pavers. New pavements are typically laid at 600 to 1,000 square metres per day. Relaying rates are typically 200 to 250 square metres per day. Note that the machine picking the pavers up in the 1 metre square pallets, that would not be possible unless those pavers were interlocking, and that's without the interlocking, that's without the sand that goes in between the pavers. So they're highly interlocking in nature. These photographs show the Moorebank import-export terminal consisting of 20,000 square metres of interlocking concrete block pavement at Port Botany, Sydney, designed using the Design Pave software. I'll now focus on permeable paving and its potential for both stormwater treatment and hosting and reuse. In this photograph, you'll see a 5 metre by 3 metre standard Australian car space constructed at our UniSA Mawson Lakes campus. What you're looking at is not just a place to park your car, but it's also a 4 kilolitre rainwater tank by nature of the permeable pavement system. I mentioned water treatment. The two graphs on the right hand side show the quality of water compared to a control being an experimental system that does not include the permeable pavement, and the left-hand bar in each of the graphs shows the control not changing with time. The time is shown in hours. The effect of storing water in either calcite or dolomite is to buffer the acidity and increase the alkalinity of the water. This is very important in terms of reducing the mobility of heavy metals. And the bottom graph shows the same water quality time period for dissolved zinc, which is one of the hardest heavy metals to remove from urban stormwater. And you can see that after 24 hours, the zinc has been, dissolved zinc has been removed from the permeable pavement system. So those are very encouraging results. I'll now take you through the construction of that very same system. The excavation cost $5 Australian, 450 of which was getting the excavator, incidentally. The gravel costs between $260 and $700, depending on which type of gravel. Dolomite being the cheapest in Adelaide, and that cost $260. The high density polypropylene liner comes welded to the shape of the hole, and that costs $400 to deliver to site. The pavers cost $500 and the bed and gravel cost a further $200, and the total material cost for that car space and 4,000 kilolitre rainwater tank was $2,200 per car space. Very affordable. This has shown the simple costs of a small residential system, but what about the cost benefits of other larger systems? The most comprehensive study of whole-of-life costs was undertaken in 2006 in the UK and involved 250 separate projects that were all redesigned and reanalyzed for both asphalt and paving systems. The results show a whole-of-life analysis that pretty much summarizes that permeable pavements are, permeable or interlocking concrete block pavements are, in terms of whole-of-life, better than asphalt pavements, other than in initial costs. And it's usually the initial costs which dictate which way a design will go, which is unfortunate because when you look at normal discount rates between 5 and 10%, asphalt in 250 projects was less beneficial environmentally and economically than concrete block pavements. You had to raise the discount rate to over 15% before asphalt becomes more competitive. So that's a whole of life cost analysis. What about the environmental performance? Well, one of the benefits of both permeable and interlocking concrete block pavements is their performance in terms of heat island mitigation or amelioration. Asphalt has a very low albedo, predominantly because of its black color, and so it absorbs more heat and radiates this back both during the daytime and the night time. In a Japanese study during the Japanese summer, a paving system reached a maximum temperature of 40 degrees C during the day, while a comparable asphalt system situated adjacently reached a further 18 degrees higher, 58 degrees centigrade. That gives you an indication of what these systems, what happens with these systems. When you compare the performance of PICP, which is permeable interlocking concrete pavement, with asphalt and with porous asphalt, there was a stark. During the day, which is the left-hand bar in each case, there was a threefold increase in the daytime sensible heat flux for asphalt and porous asphalt. And this was mirrored at night. While both were lower, the asphalt and the porous asphalt still radiated 3 times the heat that a concrete block pavement radiated out. So this is further evidence that the environmental performance of permeable and interlocking concrete block pavements is better than conventional asphalt. A further answer might be to use carbon neutral paving with natural air conditioning through evapotranspiration. A typical tree may capture 20 kilograms of carbon dioxide per annum, or 1 ton over a 50-year period, 50-year lifespan. Therefore, 1 tree per 11 square meters would be required to offset a concrete segmental pavement or a permeable pavement to make it carbon neutral. Most engineers, though, would cringe at the thought of integrating tree roots with paving systems, but this is largely unjustified for permeable pavement systems, as I'd like to show you. These photographs are taken from Dr. Tim Johnston's field experiments conducted for his PhD at UniSA. They show juvenile ornamental pear trees planted adjacent to permeable pavement systems located in heavily reactive clay soils in Adelaide. His 4-year study traced and mapped the root architecture that developed in these trees as a result of watering from the permeable pavement. Only opportunistic fibrous roots were found in the base course because this layer dries out so quickly. So those fibrous roots never grew into more substantial woody roots. More permanent woody roots were all confined to the underlying clay subgrade, where water was retained for much longer. And that's how the architecture of the tree roots developed during that 4-year period. There's a further photograph showing these systems. I'm now going to hand over to my colleague, Associate Professor Mizanur Rahman, who will demonstrate the DesignPave software, which, as I mentioned earlier, can be downloaded free of charge from cmaa.com.au. Thank you.
Thank you, Simon, for your presentation and insights. I'd now like to welcome our second speaker, Dr. Mizunur Rahman. Dr. Rahman is an Associate Professor in Geotechnical Engineering. He has a strong track record of fundamental research into many aspects of geotechnical and pavement engineering, with the support of prestigious fellowships and federal state government funding. He has been successfully translating his fundamental theoretical research into industry-partnered engineering applications for liquefaction assessment, pavement engineering, recycling materials for the circular economy, soil reactivity and failure of buried pipelines. The results of these research studies have been published in many reports and more than 150 peer-reviewed articles. He has maintained high-level professional engagement in both academia and practice by being an editor-in-chief and editorial board member of several international academic journals. He's also a current member of a number of technical committees of the International Society for Soil Mechanics and Geotechnical Engineering. As part of his pavement research, he recently also authored the DesignPave software, which is now the national standard software for the design of interlocking and permeable paving, and is freely distributed through the Concrete Masonry Association of Australia, CMAA. Please welcome Dr. Mizunur Rahman.
Hello everyone, my name is Mizunur Rahman and I'm also from the University of South Australia. I'll be discussing a bit of pavement theories and demonstrate DesignPave software for which I was leading a development team supported by the Concrete Masonry Association Australia. As Simon mentioned earlier, the top layer of these pavements are rigid paving blocks and they can be pervious and impervious depending on applications. For heavy-duty paving system, pavers are laid on bedding sand and the design is dominated by mechanistic design. For the permeable pavement, pavers are laid on coarse material and design is dominated by hydrological design, as you can see in this figure. However, DesignPave uniquely combines both mechanistic and hydrological design in a single platform. It also combines several design approaches, for example, single equivalent axle load or minors rule for individual axle load. Particularly for industrial application, it also combines minor rules or single equivalent wheel load or British port method, so that the designer can compare different design approaches. It also allows designer change the wheel pressure if they want to. It also has detailed documentation, that is, it's not a black box, you know what is going on behind it. And it has a detailed reporting system as well. DesignPave is a Bosniak equation for a stress strain calculation at the bottom of each layer. So a multi-layer paver system must be translated to equivalent homogeneous subgrade space. For example, we have a multi-layer pavement system over here, which has different stiffness. For example, subgrade is 100 megapascal, base course is 300 megapascal. Using equivalent thickness equation, we can translate that one to equivalent 100 megapascal stiffness. This is subgrade and this is base course. Now we can use Bosniak equation to calculate stresses at the bottom of each layer. When we combine this calculation for different layer, then we can calculate vertical stresses along the depth of the pavement. This calculation we compare with the finite element approaches. The solid line is the equivalent thickness method and the red line is the finite element method. There is slight differences. However, when we calculate vertical strain by finite element method and equivalent thickness method, they are very pretty close. The differences over here is not significant compared to empirical equation used in pavement design. So we can ignore that. And probably this is one of the reasons we cannot use the advantage of finite element method in pavement design. Now, interlocking paver is slightly different than conventional pavement. So we need additional consideration for interlocking paver design. Shackle using falling weight deflectometer data identify this paver system develop full stiffness between 5,000 to 10,000 load repetition. This also depends on loading spectrum. Over here in this figure, left-hand side, I show the axial load repetition in y-axis and axial group load in x-axis for different standard loading. For example, this one, single axle, single tire, single axle, double tire, tandem axle, double tire, tri-axle, double tire. Now, damages for this individual axle load has to combine via minus rule and then compare with a damage law very commonly used for interlocking pavement by Edward and Velcarin. When you combine this, then we can calculate design thickness for the pavement. The figure on the right hand side, the x-axis is equivalent external axle load and required base course thickness for this traffic spectrum. As you see, if the pavement reach full interlock in equivalent standard axle load of 10, then the required thickness is smaller. But if the interlocking takes higher load repetition, the thickness increases. This is very important aspect of interlocking pavement design. Now notice, the shackle observed interlocking develop between 5,000 to 10,000 depending on loading spectrum. That's actually somewhere here. This to make the software conservative by a default interlocking load repetition 10,000 used in design pave, but the designer can change this value as they wish. Now I will show the flowchart of the design pave. When you start the design pave for interlocking design, then you come up with two options, that is design pave or analysis. Analysis could be used for forensic investigation of a pavement failure. For design, when you get into the design option, then you have two options, road design or industrial design. For road design, we could use equivalent single axle load or annual average daily traffic. Industrial load also depends on the vehicle type as well. So when you get into the design page, this is the main window of the design. I will discuss this a little bit later with running the software. When you get into the pavement, permeable pavement design, then you have come up with two options, ARR 2016 or ARR 87. This is the most common approach. I will show you when I will show you the software. ARR 2016 actually consider possible 10 different rainfall area. So when the software use these options, it comes up all possible combination. So I'll explain this a little bit later again. This is the reporting option. The detailed reports can be produced by design pave. Now, if you want to use this software, you can register and get a free copy of design pave from the CMMA website over here. Install and run the software. What I will do now, I will show you a few examples of mechanistic design. For example, when you design a road using annual average daily traffic, how to design that, or industrial pavement with different vehicle category, I'll show you these. For hydrological design, I'll show you runoff control, water harvesting, and water quality. Let's run the software. Now I will run the software design pave. So when you run the software, this window will come up, so you have to accept it. Each license for this software is pre-developed based on the user. For example, all my details comes from the license. Let's create a new project. So when you create a new project, you have to put some details that will pre-generate in the report. So for example, let's say I put new 2, new 3, new 4. So when you get into the software, it comes up with two options: design pave, which is designed for interlocking. So first I'll show this part, and then palm pave, that is designed for hydrological design and also combined with interlocking. So let's get into design pave. As I said, you have options for design or analysis. I'll show you the design today. So when you get into design, you can go to design for roads or industrial pavement. So let's get into the road. We can design for equivalent standard Excel load or annual average daily traffic. So let's get in annual average daily traffic. When you get that, you would be estimating what would be AADT. With this input parameter, you can calculate that. So let's go on. It's predefined, but you can change all these details. Now, when you come up over here, you need to estimate what would be the standard subgrid CBR. It could be 4, or if you have a linear, it's a linear structure, so you could have a series of CBR. So you could put over there and calculate the best possible case. The design we go with traffic spectrum. Let's check this traffic spectrum. So calculate over here and go ahead. We have 3 different options for design. So you could choose any of these. Now, while I'm going through these, you note that we have a detailed documentation to guide you with the software. For example, if I go for this page, what is page doing? So it's actually generate the PDF. It actually tells you what you have to do over here. It also explains the theories in relevant sections. So let's go with this one. So this is based on traffic spectrum. So this is the traffic data. So I can actually, if I want to, I can change to any spectrum. For example, if I go over there and let's say I choose this one, load the spectrum, it's the same spectrum. Show the graph. So the graph is generating another window. So this is the spectrum load I have. And based on that, we'll be designing the pavement. So go next. Now, if we design the pavement, click this button. Now over here, you notice like these are the paver thickness that could vary 60 to 120, depending on the ranges, depending on the material properties, whatever you choose. But whatever the guide you got over here, it's coming from CMMA. So design. So this is the design thickness you got. Now we can also develop a design chart. So if I click on that, so it's developing the design thickness for varying traffic load. What I realized in Australia, material cost is insignificant in compared to traffic load. So it is pretty handy to know if the traffic load increases by 10% or 20%, what would be the thickness I would be expecting. Now you notice this is not a smooth line. It's a step line for every 5 millimeter increment of thickness. It's a pretty lengthy calculation going on behind the software. So it generates all the data and trying to process in Excel file. So it's actually develop the data and trying to save an Excel file. I already have some data, so it's asking whether I want to add this data with the previous data. So we can add that. So when you go on with that, then we can also do a calculation for cost. So let's go ahead. And then you have to save the file. So let's say save it as test1 and run. This helps you to generate the report. So if you click on it, generates the PDF report. So you can see Whatever the details I put at the beginning, I put new, new 1, new 2, new 3, all comes over here. My license details, all the calculation, all the data, and all the theories required for this design calculation. Sometimes this is pretty standard. People need to customize their report. So we also have an option for Word report. Then you can modify the report as you need. So we'll keep it over here. So this is pretty much for the design of road. But if we want to design for industrial pavement, let me show you how to do that. So again, go to design pave, go over here. So we go design industrial. Then we have options for severe and the different type of industrial wheel load. So we could actually tick all of these if we want to. If something is not here, then we could have a customized vehicle type. So go next. Now, sometime for industrial loading, we could have container load. This is a spectrum for container load. We can change that. Let me see what is the container load over here at the moment. So this is the spectrum we have. So calculate the critical load and go ahead. Now, once you do that, whatever the vehicle type we choose earlier, it comes over here. And these are pretty standard predefined configuration of the wheels. It could be changed, so you could modify that. If you want to know what are those, again, you can go to the software, and software will help you. For example, I often forget what is this. So D is this one, X is this one for this type of wheel load. Go next. For industrial loading, the dynamic factor is very significant. So you could have different kind of dynamic factors. You can choose all of these. You can modify all of these. Go ahead. So once we do that, it calculates what would be the individual wheel load. So it gives all these details over here. Now, once you come over here, you could design the industrial pavement based on Miners rule or single equivalent wheel load or British port method, whatever you choose. So for example, I'll show you Miners rule. So when you go Miners rule, you could design this. Again, the design thickness comes like that. You can produce a design chart if you want to. Let's go back, and I want to show you a little bit about like British port method. So British port method is like that. So calculate. It actually uses a chart to calculate the design thickness and pretty specific standard material. So you can go ahead with that, calculate the cost, and you can also generate the report. So this is the chart used for single equivalent wheel loads that also used in British port method. Now I'll show you a little bit about permeable pavement design. So if we come over here, so when you do permeable pavement design, we design for 3 different options: runoff control, water quality, water harvesting. Runoff control and water harvesting pretty similar, so I'll show you these 2 first and then water quality. So let's go on with runoff control. So when you get into runoff control, so these are the options you could actually design permeable pavement road. Let's go any option over here, residential pavement. So if you do that, then it comes with paver options. So you can look at different type of pavers. Let's choose this one. Once we choose that, it's predefined. It chooses the predefined values for this paver. You can modify this, but these are recommended from CMAA. Now you could choose subgrade material. For example, if I choose the subgrade like silty or clay, this is not ideal for runoff control. We have different measure to do that. Let's go for a sandy type material, poorly graded sand. Once I choose that, these properties are pre-generated. Let's say full infiltration design. So get in, and then these are the base course material you have to choose. When you go to different base course material, it shows what is the configuration for this material suggested by CMAA. So let's go with this one, and see it's immediately pre-populate this information. But if you want to calculate this information, for example, if I go to calculate with the bulk density and particle density, we can calculate Y ratio and use this value. So it's using that value. You can design for without catchment and with catchment. Sure, without catchment. Now, once we are here, we have two different options. ARR 2016, it's recommended, it's new. And very commonly use ARR 87. We are not using this one anymore, but we also keep this in the software if someone familiar with that and want to compare. So go ARR 2016. Now, once you go there, so this window pop up. It's very important. For example, let's say we have option for capital cities. So if you choose a capital city, then next thing you have to do, go, let's say I will design for Adelaide, go Adelaide, and AAP, let's say 5%, 30-meter rainfall. It has pre-bus data, so you could include that, or you choose not to, then that's fine, go there. Then we want a target runoff coefficient of 0.3, go ahead. And this is the data we have. So now you see in 2016, instead of 1 rainfall data, we have 10. And if you go one of these, we can see this first part is the pre-bust option. Now you could design with the median peak inflow, or you could choose any of these. So if you choose any of these, go ahead, go on. Now over here, it asks you, once you have completed hydrological design, it asks you whether you want to do mechanistic design as well. So let's say yes, new, and you could again design for road and keep continue the same process. Let me show you because it will generate some information. Let's go traffic spectrum again. I quickly pass that because when you come over here and you are designing permeable pavement, then you do not use cemented or stabilized material. So these options are inactive. You cannot use this base course. Go next, design. You could generate a design chart. We are not interested anymore. Go next. Now over here, it tells you the base course thickness for mechanistic design is 180 millimeter, whereas palm paves or palm hydrological design says 100 millimeter. Now you could choose one of these. So we said, okay, we'll go for mechanistic design. So that thickness comes over here. It tells you all the configuration of the material over here. So for example, if you want to know what is the configuration, the link is given over here. This is the website. It gives you all the details. Now, I want to show you another very unique option in design pave. Instead of the capital cities, you can actually choose any location in Australia. So for example, if you know any location where you could get this information of IFT, you could use a BOM website to download their data. You can also use BOM website to download their pre-bus data. And once you get this data, you can put into the software and it could design, do the calculation. For example, if I go over here, so this data for Mawson Lakes, where my campus is. So over here, you see all this information there. You just need to download this data. Let me show you the download options. So over here, you can download it as CSV. This morning, I downloaded some data, so I can show you how it works. So for example, I choose a specific city and mountain lakes in Adelaide. So I just put ML, and then IFG data I put somewhere in my desktop. So design pave data. So this is, so data is selected over here. Now, if we want to use pre-bus data, you can download again and pre-select. It's done. We want to see pre-bus events, so keep it. This is the data we got from Mountain Lakes. It's maybe the same data as I showed you before, because that is the default data we made for the software. You can use for this design, and you can go ahead with mechanistic design or not, you choose. The other option for this design would be water harvesting. So go to water harvesting. It's slightly different. So let's go residential pavements. So if you go there again, you can choose all these details. Over here, you need average annual rainfall data, and you can modify all these over here. Let's say we need we want to harvest 100 liter per day. Let's test, save this one. And choose Adelaide, calculate. So it gives you several options of design. So if we want to get 100% solution, then the required base course thickness would be 275 milliliter. But what is be the optimum design? It would be 88.3% of the solution, total solution. In this case, the base course thickness would be 100 millimeter. So you can harvest 100 millimeter liter of water per day. If we go 275 milliliter base course thickness, but we would get 88 liter per day harvesting if we go 100 millimeter base course thickness. So this is most economical design. So you could choose one of these. So choose that. Go. Again, you could choose whether you want to do structural design or mechanistic design. No, and you can go ahead. Now I'll show you how to design for water quality. So go back to Permeable, and this is water quality. So let's go on. Again, we'll go residential pavement. Good, good. Now over here, again, you can choose average annual rainfall. And we want to improve water quality for suspended solid, total phosphorus, and total nitrogen. And we want to reduce 80% of total suspended solid, 45% of phosphorus, and 40% of these. And reduction coefficient, you have to choose. You can put yourself, or you want to calculate for equivalent number from music software. You can do that. So for example, I show you, we go that one. It tells how we combine some information from music. Let's calculate and use this value. Then it will come over here. For example, this one, again, calculate, use these values. Again, calculate. And now we want to do all of these. So it says greater than 90%, 95% of the runoff has treated. So these are the design options we come up. Go ahead. We want to do mechanistic design now. Go ahead, calculate, and then we can generate the report over here. When you choose to include mechanistic design, then the report will generate information for mechanistic design. So that's all from my software demonstration. Thank you. And now Shushu Zhang from Baker will share her practical experience of designing innovative heavy-duty pavement system, including airfield application. Thank you.
Thank you, Mizzen, for your presentation. Our final speaker for the evening is Shushu Zhang, Senior Associate Civil Engineer at Becker and a senior member of the Becker Airports team. Shushu is a chartered civil engineer and has special skills in airfield engineering design and project management, and has held key roles in airfield development projects in Australia, New Zealand, and the Pacific Islands. Shushu specialises in heavy-duty pavement design for airfield, and she will talk about the application of interlocking concrete block pavement on airfield. Please welcome Shushu Zhang.
Hey everyone, welcome to the webinar. I'm Shushu and I work for Becker in the Auckland office. I specialize in airports, and today I'm going to share with you the application of interlocking concrete block pavement on airfield. You may wonder, where have we used interlocking concrete block pavement or ICBP being used on airfields? Well, it is primarily used on aprons. This is where a majority of the movements will be really slow movements, as you can imagine, and static loadings. So typically concrete pavement is preferred over the conventional flexible asphalt pavement. ICBP was first used in the UK in the 1980s at Heathrow and Glasgow airports. In Hong Kong International Airport, over 450,000 square meters of ICBP were constructed on their apron in the 1990s. In Australia, the first application was used in 1989 at Cairns International Airport as a trial on their domestic apron. Subsequent to that, over 15,000 square meters of ICBP were built on their international apron over 3 parking bays. It has also been used at Sydney International Airport, RAF Base PS and Tyndall. In New Zealand, Christchurch International Airport reconstructed their gate 26 and 28 in 2011-12 using ICBP as inserts. So why do we use interlocking concrete block pavement on airfield? Well, it is an alternative to the conventional Portland cement concrete. As mentioned earlier, concrete pavement is performance better, so it's typically specified on aprons. The construction speed is a lot quicker for ICBPs because the curing time involved is much less as the blocks has already been manufactured, and it's less weather susceptible as well. Refueling is a major activity on the apron, so the pavement needs to be fuel resistant. Concrete pavement performs much better than flexible asphalt pavement in this aspect. The maintenance for ICBPs are typically lower compared to other conventional pavements, as you could just replace the blocks in segments or slightly larger area dependent on the defects. ICBP is also a good pavement candidate if your site is subject to differential settlement. This was the case for the original Hong Kong International Airport, as the site was built on reclaimed land. The predicted settlement over time, over 30 years, was up to 500 mil, with a differential settlement expected between 200 to 300 mil. So the blocks could just be relayed once over time to the correct level as required. The blocks we typically specify on airfields is the 80 mil type A blocks. So these blocks, as you can see to the right, have weaving edges. So this is to provide the interlocking application. These blocks are typically placed on 20 mil bedding sand on a layer of a geotextile. We often specify a stabilized base, and this could be in the form of a cement treated base course or lean mix concrete. Sometimes you may need another layer of fine crushed rock underneath, either due to undercut or slightly weaker subgrade. As you can see on the to the right, on these snips, so the blocks are laid in a herringbone pattern, and then where you have service manholes or pits, the blocks are typically laid perpendicular to the edges. A cross section to the bottom right shows the 80 mil blocks on 20 mil bedding sand on a substantial layer of lean mix concrete. This type A blocks is the only type that is suitable to be laid by hand for heavy-duty loadings. The design standard and guidelines that commonly referred to ICBP is the UK Defence Estate concrete block paving for airfields, as shown to the left. Australian standards also have a set of design manuals, as you see on the screen. Also, the Concrete Masonry Association of Australia also have a set of publications that specify the segmental pavements. These documents include the design considerations and the construction specification used for the block pavers. Here are some photos and show the completed interlocking block pavements on aprons. So the typical type A blocks with weaving edges and laid on herringbone pattern with services pits in there as well. Paint marking just applies as per normal to other type of pavements. Those photos were taken for the Christchurch International Airport Gate 26 reconstruction. Top left photo shows the curing sheets and the plastic sheeting on top of the Limix concrete, just as a curing with sandbags holding it down. The other three photos show the various stages of the block paving getting laid. These were laid by hand, as you can probably tell from the photos. The bottom right photo just show the straight edge being used to check the surface levels and the blocks being laid in herringbone pattern, as mentioned previously. These close-up photo shots show the typical details of the block pavers at pavement edges or surface trenches or surface pits. You could use different types of blocks, as you can see from the photo here. The straight edge were used at the edges. These are laid perpendicular to the surfaces, edges, manholes and edges as well. Here is a fragment of the time-lapsed video for the Christchurch Airport Gate 26 reconstruction, courtesy to Christchurch International Airport and Foten Hogan. Baker was the design consultant for this project and Foten Hogan was the head contractor. Here's the fragment of the time-lapse video. As you can see, this layer of Limix concrete was poured and the hessier mats were placed on top as a curing layer, and plastic sheeting with sandbags were used just to hold it down to keep the curing in place. The original pavement was in asphalt, and this extent was over the main gear parking area as well as the nose block. While they waited for the curing to occur for the Limix concrete, they are reconstructing the asphalt tie-in edges, as you can see from the video. Once that's all completed, the curing mats and the hessier mats were lifted up. And the pavement was cleaned and let dry. And then the layer of geotextile were laid over the entire area above the Limix concrete. Bedding sand were delivered in bags to site and was just dumped and laid out. The block pavers were delivered to site on pallets, and so you can see from in the middle of the video. bedding sand was spread out. These were generally 20 ml of bedding and compacted well as a buffering layer. And to the far left, you can see the blocks were placed by hand in transverse direction. Sealing sand was applied, as you can see, just to fill all the joints. The joints are typically about 2 to 3 mil, and these sealing sand were just to fill in the gaps. And then the final sealing layer is applied to hold it down so that the sand is not eroded away or jet blasted away. So what to look out for those blocks? Those blocks need to be manufactured quite high quality. You typically need several molds during our production so that the block dimensions are maintained. If you don't maintain the block dimensions, deficient joint spacing could be the result. As you can imagine, if the blocks were slightly, the joint is slightly too large than specified, then you lose that interlocking ability. If the joint is too close, i.e. the blocks are butting up against each other, once it's loaded by the wheels, aircraft wheeled up to about 30 ton per wheel, those blocks are going to crack up and rotate and sprawl away. So these need to be quite carefully designed. The joint tolerance is typically quite small, between 1.5 to 2 mil as a tolerance. So careful attention to detailing is required. As you've seen in that video previously, a bedding sand and the jointing sand was used. So those sand needs to be of very high quality. Otherwise, you're going to end up having a rocketing surface, which no one wants to have on the airfield. Unlike the application on roads or pedestrian pavements with the permeable blocks, we actually do not want the blocks to be permeable on airfield. This is because of the subbase, and subgrade is very moisture sensitive. And if there's too much water entering the pavement, we could end up having shape loss and a defect pavement. So that's typically why we specify a lean mixed concrete layer underneath or a cement stabilized layer underneath. And the geotextile was used just between the sand and the base layer so that it doesn't get migrated into. As you've seen in that photo, in that video previously, the blocks were laid by hand. So this would mean the performance relies heavily on the quality of the workmanship. The blocks can also be laid mechanically, subject to review of the methodology and the engineer's determination, but seems to be the common practice in most of the projects that these were laid by hand, just to control, make sure all the joints, etc., are all met for the standards. As similar to other pavements, regular maintenance would be required for block pavings. Typically, the joints need to be resanded every few years, maybe 5 to 7, with some regular replacement of the blocks at about the same duration. Major replacement of the blocks is expected about 25 years and full replacement at about 40 years. To sum up, interlocking concrete block pavement, or ICBP, is suitable for use on aprons as an alternative to the other types of pavement. There's no major curing required for the blocks as they're already been manufactured out of the factory. It is less weather susceptible, hence overall shorter construction than the conventional Portland cement concrete. The blocks are fuel resistant, therefore it's a good choice on apron. The maintenance is typically lower compared to other type of pavements. It is a good candidate, good application for use on site where differential settlement is expected. As mentioned earlier, the blocks can be laid mechanically or by hand, with the latter appear to be specified more often. As such, the success of the block pavement application on the airfield highly depends on the details specified, the workmanship of the labour, as well as the quality of the materials. Thank you.
Insights and sharing some great case studies on what is quite a complex topic. It's now your turn to get involved and to raise some discussion and debate around this. I want to thank everybody who has already sent through questions via the registration process. If you do have a question now, thank you for people who are putting questions into the chat box. That's the right place to do it. And it would be great if you put your name and also if you'd like to direct your question to a certain person. We've got 20 minutes of Q&A, so we'll make the most of it. My first question did come through on registration. It's been directed to Mizan, and it's from Deng, and Deng is based in Victoria. And talking about councils, so council nowadays ask for permeable pavers, and some have their own indicative design, which has been a real constraint to us for alternative solutions. What should we present to council to get them to agree on other alternatives? Listen.
Thank you, Dang, for your questions. I know the design has to be customized per council. You can do design customized two different ways. One is actually customize the design according to council requirement. So I can share my screen and show you how to do that in design tab. So if you go to design page, and if I go to design, let's say any of these design, over here, if you want to modify the design parameter according to requirement of City Council, so you could do that within this software. See, this software has recommended number for default material, but you can change these to an advanced design option. When you do that, then basically you are free to choose any parameter for design. So that is one unique feature within this software. And the other option we discussed during my presentation is when it goes to reporting. So if you generate a report in a Word format, so this software allow you to modify the report whatever the way you want. So if City Council are interested in particular design calculation, then you probably can show them that design calculation. So I have shown that anyway. So this is how you can actually customize the design. One is through the reporting, and the other one is manipulating the design parameters. Thanks.
Oh, thank you for that. That's great. We have got a question from George, and George, thank you. You've sent in a few questions, so it's great that you're so engaged. But one that jumped out for Simon in particular was George is asking, what are the maintenance requirements for a permeable pavement over a 25-year design life? Simon.
Thank you, Amanda, and thank you, George. That's a great question, and it's one that is very commonly asked. Probably the two Two ones that we get most often is about clogging and how to mitigate or ameliorate it. And the other one's about the strength of permeable paving in particular. In terms of clogging, there are a number of approaches and almost philosophies that you can adopt. One of which will sound probably very surprising to most people, and that is you can have a zero maintenance regime if the design is undertaken accordingly. And what I mean by that is from a number of field studies, both in Australia and overseas, there's been a very, very careful examination of the decay in, or the decrease in infiltration in permeable pavers over time, over years. And we've got a very good understanding of how fast that occurs for different catchments. And what you can do is actually use the lowest asymptote of that decay curve, the lowest infiltration rate that will ever get measured on that pavement. You can use that as your design infiltration measure. And if you do that, you're actually saying, I'm allowing this permeable paving to fully clog, and it will still function and it will still work over its entire 25-year life. It means you end up with a bigger permeable paving system than you may actually need. But if space isn't a constraint, that might be a good solution because you will have no maintenance issues. It's very controversial as an approach, but it's one that's been published and is quite acceptable as long as it's done properly. Much more commonly, though, councils ask for maintenance regimes for permeable paving because they do decay with time in terms of the infiltration rate. And there's sort of three approaches you can then adopt. The cheapest, and by the way, of these three, they're all as effective as each other, quite frankly. But the cheapest is sweeping, periodically sweeping the joints between the pavers, and then maybe relaying a bit of joint material back in, because you might sweep out some of the joint material. And that usually is done every 2 to 5 years, depending on, you wait until you see clogging and you wait to see ponding on the permeable paving that indicates the clogging's occurred, and then you'd sweep that paving system when that occurs extensively. That's the cheapest way. Second way is to vacuum, so you can actually suck out the collected debris and silt from between the pavers. Usually there's a third approach as well, which is to suck and also to wash as well at the same time. Sorry, wash first and then suck the water which has the silt bonded to it. You would have thought, common sense would have said that's probably more effective than sweeping. The literature and the field studies that have been undertaken don't actually demonstrate that, and that sweeping is just as effective. And that's largely because most of the material that causes the clogging is actually in the very upper layers. So when you sweep that out, you've got a pretty effective system left, as long as you do replace the material that does get swept out. So there is a fourth option, which is probably the most expensive of all, and that is you wait again. You don't over-design your pavement, which was the first option, but you just wait for it to fully clog. You then, after it's fully clogged, go back, lift all the pavers up, sweep away all the old bedding material, which is where all the silt will be collected, lay fresh bedding material, which is very cheap, and put the same pavers back down again. And that basically results in a brand new pavement. It's a lot more expensive than sweeping, but it is another approach. Okay.
Thank you, Simon. And before we bring Shushu in for our next question, with a great login of apple juice, and this is another one that Simon picked up that came in through the chat box. And the question is, how can you prevent upward pressure coming from buried tree roots that pushes out the interlocking pavers that cause trip hazard and deformation of the pavers? Simon.
Thanks, Apple Juice. That's another common question we get, and in my presentation you'll see that I did mention about permeable pavers and tree roots. So I'll start with permeable, but then move on to interlocking impermeable paving systems, because that's where the problem really predominates. But with permeable paving, as I showed in the presentation, you can even plant juvenile trees, and the root architecture, if it's properly designed, will grow down into the underlying layers below the base course and will not cause lifting of the pavers, and that's been quite clearly demonstrated. So as long as you keep the system dry, the roots are opportunistic. They go for moist areas, and they'll head towards where the moisture resides for longest. Okay. But in interlocking paving systems, it's a bit different, because you can't prevent the sand and the base course material, which is usually graded in an interlocking system, whereas in a permeable system, it's usually uniform size, the base course. So the moisture hangs around for much longer periods in those systems. And that's where tree roots can be problematic. And historically, the councils have had a lot of problems for that. Basically, if you build a system around a mature tree, the root architecture should be already formed, and you shouldn't get any lifting of pavers, even in an impermeable system, if it's around an existing mature tree, or if you import and drop in mature trees. Palm trees are quite often imported and put in as fully grown trees, and their root architecture, their root ball effectively is fixed. If you put in juveniles, which is usually what happens in practice, your main option for interlocking pavers where you're going to have that root problem is to use a root barrier system. You don't need that root barrier system in permeable paving systems, but there's a number of commercially available root barrier systems, which are effectively like sewer manholes, and they go around the root system and they force the roots to keep going vertically downwards rather than out laterally. So that's your options for that.
Thanks, Simon. We've had a great question that's come in from Ali, who's in Queensland, directed to both Shushu and Mizan, but maybe we'll start with you, Shushu. But the question is talking about the late Professor Brian Shackle, who published many papers in the CBP proceedings and found that the number of publications and industrial applications of CBP has decreased. Is there any technical issue in the use of CBP in Australia? Note that the use of CBP as an alternative pavement has decreased in Japan and the United States too. So I hope that's a good question for you, Shushu, as you are actually in Auckland.
Yeah, I'll touch base just on the application of that in the airfield space. So ICBP is still being considered as a valid type of pavement for the airports. But often these days, we provide the clients lots of type of pavements, ranging from flexible to semi-flexible to traditional Portland cement concrete, to sort of semi-other type of stabilized, and with ICBP as well. And often we consider the whole life cycle of cost, the contractor capability, the availability of the local materials. So with those kind of factors considered together, ICBP unfortunately usually does not stand out. And that's probably what I've seen as a decline in the application in airfield.
Thank you. And Mizan, do you want to comment on that too?
Yes, Simon and I was having a discussion about it. We believe, like, in terms of technicality, there is no problem. More publication we see in journals. In the past, people liked, particularly late Professor Brian Shackle, published a lot in conference proceedings. But now these days we see lots of publication in journals. Yeah, that's my comments.
Yeah. So Mizan's spot on. So it will appear as if there's less conference papers on permeable paving. There are still people who publish in conferences, but it's much less common. And most academics now prefer to use peer-reviewed journal papers because you get feedback from other academics and practitioners. And so if you were to look at the body of work that's published yearly now in permeable paving, or in interlocking concrete paving in the journals, you'll see that's much increased since Brian was publishing in the 1980s. So it's horses for courses, really. It's really where they're being published rather than the number that's being published.
Thanks everyone. We've had a great question come in from Yuan in New South Wales, directed to Shushu first and then Simon, if you also want to comment, and asking why is sand important for this type of construction?
I'll go for first. So for airfields, as you've seen, there's 20 mil bedding that's used below the 80 mil blocks. And typically below that, we use a rigid sub-base or base. And then that 20 mil bedding just provides a cushioning layer. Otherwise, you end up having concrete blocks butting up against a rigid pavement. And so that sense bedding is quite important for airfield application. Also, the sand is very important to seal up the joints as well. Otherwise, you end up having this 2 to 3 mil joints that's potentially just going to make the blocks move or have vegetation grown up. So that's why it's really important. The sand needs to be specifically suited for that very purpose.
Simon, do you want to comment on that?
I'll just add to Shushu. I agree entirely with what she said about interlocking concrete block pavements. When you deal with permeable pavements, though, you must be careful not to use sand as a bedding material or a jointing material. You have to use fine gravel, usually 2 to 5 mil gravel, and there's very good reasons for that. Because most engineers have more experience with the impermeable pavement systems, they tend to get into that habit of using sand, which is the right thing to use. But when you move across to permeable, you mustn't use sand. It clogs far too quickly and it has a number of other disadvantages. So we use 2 to 5 mil bedding gravel, which is harder to compact, and in fact, virtually you can't compact it compared to sand, which is easily compacted. But it is much better for the hydrological performance of the permeable paving system. So sand for impermeable systems, 2 to 5 mil gravel, bedding gravel for permeable systems.
Thanks, Simon and Shushu. Just staying with permeable, we've had a really interesting question coming from Jordan in New South Wales, asking you, Simon, have you found it difficult to convince clients to use permeable pavements considering increased costs?
Great question, Jordan. Answer is yes. The reason it's yes is because people only look at the initial costs. If they were to look at the whole of life costs, permeable paving or interlocking concrete block paving is generally superior, both economically and environmentally. And that study that I showed in my presentation, in my slides, is the most comprehensive. 150 projects were reanalyzed, and it was a uniform response that paving systems are superior to traditional asphalt systems. And then when you add in the environmental effects of urban heat island effects, it's incredibly superior as a system. But people don't look at whole of life costs, unfortunately. We tend to look at things as particularly clients, they tend to look at it as how much they have to pay for their system to be installed. They don't look at the long-term maintenance and other costs and replacement costs. And if they did, then a lot more paving systems will be used. So it's a question, a philosophical question almost. Do we pay for it or do our children pay for it? It's that simple.
And is automation changing that dynamic?
Education to a certain extent. As the systems become more and more popular, people's mindsets will change. In the UK, just for interest, you cannot build a Coles car park or a Woolworths car park or a hospital car park out of impermeable material. You just will not get permission to build. You have to demonstrate permeability. So all their car parks are going in now, large-scale outdoor car parks in those types of developments as permeable systems. And the clients are on board with that. They understand the benefits. We're some way behind that in Australia.
Thanks, Simon. And we've had a question that's come in a few different ways, and hopefully I'm doing it justice, but I will use Jonathan as a trailblazer here. And Jonathan's based in WA. Hi, Jonathan. And Jonathan's asking, amongst others, have clogging factors over time been considered in the use of permeable pavers? And has the infiltration rate on various grades been reviewed? Is there any feedback available on varying performance? Thanks, Jonathan. And maybe Simon, Shushu, whoever wants to pick this up.
I can start if you like. In terms of runoff of pavers, for permeable systems, there shouldn't be runoff if they're designed appropriately. So there is no effective runoff factor for permeable pavements. It doesn't come into the design, I should say. In a well-designed interlocking concrete pavement system, impermeable system, the key word being impermeable, the runoff is, it's not 100% because there's a wetting that occurs and there's evaporation that occurs, but they're so small compared to other hydrological losses that most engineers would take a conservative approach and assume that the surface is fully impermeable and it will be 1.0. Just to illustrate that, a metal roof on a house, you would have thought that's definitely 1.0 runoff factor. It's not. all the measurements that have been shown is that not 100% runs off, because some gets held up on the roof surface, some evaporates, and some is used for wetting effectively. So there is no such thing as a runoff factor in practice of 1.0, but most engineers, and Shusha, you can correct me if I'm wrong, most engineers would use a factor of 1.0 for an impermeable pavement.
Shusha, do you want to comment on that?
No, Simon's covered it pretty well. We do use 1.0 as a conservative approach for our design.
Thank you. Thanks. We've got a very specific question that's come in from Sean, who's based in Queensland, and is asking, and hopefully this makes sense to us all, but how do we get more support for this in southeast Queensland? Simon, Misen, who wants to pick that one up?
How do we get support in southeast Queensland? I would say go to people, either practitioners or academics that are working in this sphere. The networks in engineering tend to be quite local. Engineers Australia is a very good forum for that. Most Engineers Australia regions have regional offices and regional panels. So when I lived in Sydney, I was part of the Sydney Water Panel, which meets regularly, and getting to know those people is a very good way of doing it. In southeast Queensland, there is a group at the University of Sunshine Coast that works very well in permeable paving, and they in fact have been pioneers of integrating street trees. We started that at UniSA with Tim Johnston's PhD, which I referred to in my presentation, but Terry Lukey and Chris Walker and others at the University of Sunshine Coast have actually done larger scale experiments on their campus at Sippy Downs, and they've got some great expertise on permeable paving in particular, but also on interlocking concrete block paving. So I would say connect up with those in the first case. Now that's not to say there's not expertise residing at Griffith and UQ and other universities up there. I'm sure there is, but the group that's probably in southeast Queensland that's most notable is at the University of Sunshine Coast.
Thanks, Simon. Misen, just to bring you back into the discussion, we've had a great question from Edward, who's based in Victoria, asking, what subgrade do you recommend for the permeable paving to be successful in allowing water to infiltrate? Thank you.
For a runoff design, if you use our software design pave that actually guide you what kind of subgrade would be suitable for. Let me share my screen and show you again. So if you go to PalmPave software runoff control, let's say residential building. This is the paver layer, so it gives all the parameters. But over here, when you see, if I go to city and clay type material, it gives you a recommendation, not recommended for full infiltration design for runoff system. So this gives you some experience-based database. But if you try to design for sand or gravel type, it should be fine. It should be fine. Thank you.
Thank you very much for that. We've had a question that's come in asking, what is the minimum width of the shoulder of the interlocking pavement for the model to be valid? And I'll throw that open to whoever wants to pick that one up.
Well, it depends on the application, I guess. I would imagine that in the airport area that Shusha works in, I would imagine that the edge barriers have to be quite strong. But in a residential road, a standard curb is usually sufficient. So, which is much smaller application. Shusha, do you know about the edge constraints used on the airfields? I'm sorry to put you on the spot there.
No, that's all right. So for airfield applications, it's probably slightly different. As mentioned in the presentation, the ICBPs are only used on aprons. So aprons are really low speed. So typically it's 5 to 10 kilometers per hour. Usually those are just used either together with other types of concrete pavement or with an asphalt surround. And typically, as you expected with other typical asphalt and PCC interface, there's always going to be that substance or channelized rutting along that asphalt surface. So this is no difference as to whether it's ICBP or conventional PCC. you're just inevitably going to have some edge issues over time, and that's where the majority of the maintenance will occur. There's no such constraints in airfield application, really. Yeah.
And the 20 minutes has just flown by, and we have had a couple of questions, and people are asking, you know, where do they find out more information? You know, what websites to look at? You know, for young engineers that are thinking of, you know, entering this sector, this area of practice. What sort of advice would you give? Maybe we can just go round the starting with Ms. Anne.
If you follow our software, the software comes up with health menu, and that menu gives you as possible information we could access during that time. So all the papers are cited, all the available information from Concrete Masonry Association Australia, all of them are there. But apart from that, I think there is lots of published journal papers. Simon had lots of paper. And Concrete Masonry Association.
Yeah, I agree with Ms. Anne. The Concrete Masonry Association also has a very effective library database, so you can actually download papers from their website free of charge. And that's a lot of those are on permeable paving rather than interlocking concrete block paving. But there are manuals also available from government authorities, councils, and elsewhere. So there is a plethora of information out there that you can tap into, usually free of charge. And then another interesting source is actually the paving manufacturers themselves. It's in their interest to give you as much information as they can to sell you their products. so they are very, very knowledgeable, and they have very good guidelines themselves.
Thank you, Simon. And I have noticed this evening that we haven't had any questions from female engineers out there. So, Shushu, do you want to just maybe talk to, from a diversity point of view, how did you get into this, how you've enjoyed it, and etc., and advice to not just female engineers but young engineers coming into the profession?
Yeah, sure. I started about 12 years ago when I graduated from the university, and I joined Becker. And what I didn't want to do was to go into a specialised, for example, structural or geotechnical. So I chose airports, because at airports we deal with pavements, we deal with utilities, we deal with stormwater. So there's quite a broad range of services that we cover within the airport space, and I've been enjoying that so far. And I've worked on a range of projects over in Australia, over in New Zealand, and over in the Pacific. So definitely encourage more and more women to join the engineering world, and I'm definitely seeing more of them throughout online events or offline events. And the professional body like Engineers Australia, Engineering New Zealand is a great professional body to join, and that's often a great place to know your peers as well.
Thank you so much for that, and I'm sure you're very busy out at those airports where there's not a lot of people travelling right now. That's all we have time for today. Please join me in thanking Shushu Zhang, Dr. Mizanur Rahman, and Professor Simon Beecham for giving up their time tonight and sharing some fantastic insights. It's so much appreciated. We also appreciate you, our audience, being here this evening, and we'd love to hear from you. We're always looking at ways to improve and basically talk about the things that are going to make a difference to your career and the work that you're doing and the future work that you'd like to aspire to. So please, if you see, there's a short feedback form in the description box below. Once again, I'd like to thank our industry partner, Austral Masonry, for making tonight's webinar possible. A long-standing partner, we really do appreciate their support. Without industry's support, we wouldn't be able to do what we do. So thank you again, have a lovely evening, and I look forward to seeing you at our next webinar. Thank you, good night.
Products, bold innovation, brick Earthworks B20. Thursday, October 29th, 2020.